Good day. In this video, I will discuss how to derive a position vector of a given mechanical manipulator. So this is a basic mechanical manipulator. This is a 2 degrees of freedom mechanical manipulator. So this is a 2 degrees of freedom SCARA manipulator. I will teach you how to derive the position vector of this mechanical manipulator, just like what we have done in the derivation of rotation matrix. Okay, so to derive the position vector of this mechanical manipulator, we will start again from the base. Okay, we will start from the base, the frame of the base, and the next frame after the base. So the next frame after the base is frame 1. So the base frame is frame 0. Then the next frame is frame 1. Okay. So our reference frame is frame 0. So our reference frame, if we talk about reference frame, it means it is the largest frame and the most important frame, or the most important part of our mechanical manipulator. Then the projected frame is inside the reference frame. So to get the position vector of our frame 0 to frame 1, we will look for the distance of frame 1, or we will look how far is the origin of frame 1 to the origin of frame 0 along x sub 0 axis, y sub 0 axis, and z sub 0 axis. Okay? So if we look at the front view of this mechanical manipulator, we will only see two frames, or we will only see four axes of our two frames: the axis of x sub 0 and z sub 0, as well as the axis of x sub 1 and the axis of z sub 1. Okay, so the axis of x sub 1 and z sub 1 is along the axis of x sub 0 and z sub 0. This is the front view. Okay, so y sub 0 and y sub 1 is pointing at the back of our mechanical manipulator. Okay, because they are pointing at the back of our mechanical manipulator, we can't measure how far our frame 1, the origin of our frame 1 to the origin of frame 0 at the back of our mechanical manipulator. Okay, we can only measure it at the front of our mechanical manipulator. Okay, so we will look first at the axis of z sub 0. Okay, because this is the easiest part. So at z sub 0, we have here a sub 1, the link length a sub 1. Okay, the link length a sub 1 shows how far is the origin of frame 1 to the origin of frame 0 along the a sub 0 axis, because a sub 1 is a constant and it's a link length. Okay, how long or how high is the length from the base up to this point Okay, up to this point of the first joint. Okay, so our z coordinate is a sub 1. Okay, so I hope you get why it is a sub 1. Again, a sub 1 is the link length. Okay, the measurement. Okay, the measurement of how far is the origin of frame 1 to frame 0 along y sub 0 axis. Okay, this is the measurement. That's why this is indicated here. Okay. Next, we will go to the axis of y sub 0. Again, y sub 0 is pointing backward. So we can't measure the distance or how far frame 1 is to frame 0. Okay, so that's why the y coordinate is 0. Now, for x, we will look at the axis of x sub 0, how far the origin of frame 1 to the origin of frame 0. So, along x sub 0 axis, we have here the link length a sub 2. So, a sub 2 is the measurement of how far frame 1 is to frame 0 along x sub 0 axis. So, that's why we will put a sub 2 to our x element or our x coordinate. Okay, so this is the position vector. Okay, of frame 0 to frame 1. But this is wrong. Okay, this is wrong. The reason why this is wrong is because our mechanical manipulator will move. If it's moving, the theta 1, okay, the theta 1 at the first joint will have a value. It can be 45 degrees, 35 degrees, 60 degrees. If theta 1 will have a value, our mechanical manipulator will move. And because it will move, our frames will change direction. So the direction of our mechanical manipulator, what will happen to our mechanical manipulator will be look like this. Okay, it changes position. As you can see, if theta 1 has a value, it can move frame 1 to add to another position. So frame 1 changes its position. As frame 1 changes its position, the joint changes its position. The link length A2 and the link length A2 changes position. Now they are at the axis of y sub 0. Because of this, the position vector will change because it's already at the axis of y sub 0. So the new position vector is this 0, 8, 2, 0. Okay, why 0, 8, 2, 0? Because it is no more at the front view. We can now measure the distance of frame 1 to frame 0 at the back view. Okay. So again, this is wrong. Again, this is wrong. Why this is wrong? Because we should have only one position vector. Now we created two position vector. we derive two position vector. The other one is if the mechanical manipulator is not moving, and if it moves, we have a new position vector. So unlike the rotation matrix, position vector must only have one derivation. Okay? It means there is only one position vector, one true position vector, not two position vector. Either it is moving or not moving. Okay, so we need to make sure that our position vector is correct no matter what the values of joint variables are. Because our mechanical manipulator is moving, the joint variable value will change. Okay, so because theta 1 changes its value, the mechanical manipulator will move. If the mechanical manipulator will move, the joint variable value will change. So whatever the value of the joint variable, there will only be one position vector. Okay, so two approach these two approach of derivation of position vector is wrong. So we will do another approach to get the real position vector of this mechanical manipulator. Okay, what we will do is to find a way how to use Sohcahtoa in our mechanical manipulator. Why Sohcahtoa? Because our mechanical manipulator is made up of geometrical figures that creates triangles and angles. Okay? So because we have triangles and also angles, okay, the best approach is to use trigonometric functions. Okay? So we will find a right triangle to look to derive our position vector. In this given mechanical manipulator, the best way to derive the position vector is to redraw this mechanical manipulator at top view. Okay, we will redraw it at top view. So our mechanical manipulator will be look like this. Okay. This one. This is what our mechanical manipulator with frame 0 and frame 1 at top view look like. Okay, at top view, we can see a sub 2, x sub 0, y sub 0, theta 1, x sub 1, y and y sub 1, the joint 1 and joint 2, and the link A2. Okay, this link is the link A2. Okay. So this is our mechanical manipulator at top view. From this, we will find a right triangle to derive our position vector. So to have a right triangle, okay, we will rotate to the left, or sorry, we will rotate to the right. Okay, if we rotate to the right, we will have a right triangle like this. Okay, so the reason why we rotate to the right, not to the left, is because x sub 0 is positive at the right side. Okay, and y sub 0 is positive at the top, at the upward. Okay, because we need a positive, because it will be easier to compute if all our functions are positive, not negative. And also, okay, please notice the frame of frame 1, it changes its orientation from this to this. Okay, so please look for that details, that this detail means our mechanical manipulator is moving. Then it means our frames will change orientation and will change its direction, or it will change its position. So from here, it will become like this. It changes its orientation and also position. Okay. So now we have a right triangle. What we will do to is to recognize which is the hypotenuse, the adjacent, and the opposite side. So this is the hypotenuse. So it means a sub 2 is our hypotenuse. This is y sub 0 because it is along y sub 0. And this is the opposite side because it is opposite to the angle theta 1. This is our adjacent. X sub 0 is our adjacent. Okay. So now we have the hypotenuse, adjacent, and opposite. We are now ready to get or derive the position vector. Okay, so again, our position vector is denoted as P01. Okay, this is what we need to derive, P01. Okay, so X01 is the translation of projected X on the reference X. So it means how X sub 1 is translated on X sub 0. The same with Y sub 0 projected, or how Y sub 1 is translated on Y sub 0 using the rules of trigonometric function. X sub x01 is the same as X sub 0, and Y01 is the same with Y sub 0. It means if we find the relationship of X sub 0 to our hypotenuse A sub 2, we can find what is X01. The same with Y0. If we find the relationship of Y sub 0 to our angle theta 1 and our hypotenuse A sub 2, we can get Y01. So the relationship of X sub 0 to theta 1 and A sub 2 is cosine theta 1. Okay? While the relationship of Y sub 0 to A sub 2 is sine theta 1. Using SOHCAHTOA, we will derive this 2. Then, to get X01 is the same with X sub 0. So, multiply both sides by A sub 2. Our X0 is A2 times cosine theta 1, or A2 cosine theta 1 is our X01. Okay, the same with the Y01. Y01 is the same with Y sub 0. So we will equate sine theta 1 to Y sub 0 over A sub 2, then multiply both sides by A sub 2. We will get A2 sine theta 1. So our Y01 is A2 sine theta 1. Okay, so these are our x coordinate and y coordinate, or the element of x and element of y for our position vector. So now for the element of z, or the z coordinate, we will go back to our original drawing because we don't have z sub 0 in these red drawn figures. In our original drawing, we have z sub 0. Okay, so the translation of z sub 1 to z sub 0 can be obtained again using the principle of position vector from this previous lecture. Okay, so the distance of the origin of frame 1 to the origin of frame 0 along z sub 0 axis is a sub 1. Okay, it is still a sub 1 and it doesn't change because the rotation theta 1 happens at z sub 0. Okay, because the rotation of theta 1 happens at z sub 0, whatever the position of frame 1, okay, it is still a sub 1. The distance is still a sub 1 at z sub 0 axis. So our z coordinate, or our z element, is a sub 1. Okay, so this is our position vector 1. So this is position vector 1. Okay. Now, this is the correct position vector, whatever the value of theta 1 and whatever the position of the frame 1 or the orientation of frame 1. Okay, so let's go to the second position vector because we have a third frame. The third frame is frame 2. Our next position vector is from frame 1 to frame 2. So how frame 2 is translated on frame 1 or P1 2. Okay, in this given mechanical manipulator, okay, we have same method. We have we will use the same method we used from getting P01 to get P12. Okay, to get P12, we will go to frame 1 because it is the reference frame. Let's go to frame 1. So this is frame 1. This is frame 2 again. Frame 1 is the reference frame. Now, frame 1 is the huge frame, while frame 2 is the small frame inside the frame 1. Okay, so just like what we did on frame 0 and frame 1, we will redraw this in top view. Okay, it will be a bit different because frame 2 is the end effector. So it will look like this. Okay. This is the drawing at top view. Only present is the link length A sub 4, the axis x sub 1, the axis y sub 1, the axis x sub 2, and the axis y sub 2, and theta 2 with the second joint. The last frame is an end effector frame. That's why we don't see a joint at the last part of our mechanical manipulator. Okay. To get a right triangle, to use the principle of Sohcahtoa, we will rotate to the left. Why to the left? Because y sub 1 is positive to the left. So it will be look like this. Okay. Again, notice the details of frame sub 2. Okay. Frame sub 2 changes its orientation and position because our link rotates to the left. Okay. Then let's find the opposite side, the adjacent side, and the hypotenuse. So A sub 4 is the hypotenuse. This is our adjacent. Our adjacent is x sub 1. Then our opposite is y sub 1 because it's opposite to the theta 2. This is the opposite side. So our opposite side is y sub 1 because this line is along the y sub 1 axis. Because now we have the opposite side, the adjacent side, and the hypotenuse. We will use the principle of Sohcahtoa, and these are the trigo functions for this given drawing of our mechanical manipulator at top view. So x sub 1 is the same with x12. It is how x sub 2 is translated from x sub 1. So x sub 1 is equals to a4 cosine theta 2. Next, y sub 1 is equals to a4 sine theta 2. Therefore, y12 is a4 sine theta 2. For our z element, we will go back to the original drawing. At our original drawing, the distance of the origin of frame 2 to the origin of frame 1 along z sub 1 axis is a sub 3. Okay? A sub 3. As you can see, class, this is how far our frame 1 to our frame 2 to our frame 1 along z sub 1 axis. Therefore, our z element is a sub 3. Okay? So this is our position vector 1, 2 from frame 1 to frame 2. Okay. Let's put it also inside a box to indicate our final answer. Okay. So, unlike rotation matrices or unlike the rotation matrix, we can multiply a 3 by 3 rotation matrix to another 3 by 3 rotation matrix to get the rotation matrix of a whole mechanical manipulator, just like from our lessons of rotation matrices. But in our position vector, it is unable to do a multiplication of a 2 3 by 1 position vector, so we can combine P01 to P12 using multiplication. It is impossible because this is a 3 by 1 position vector and this is also a 3 by 1 position vector. The addition of position vector is possible because they have the same size, about 3 by 1, but it is not the way we will combine position vector. Okay, it's not the way we will combine position vector. The way to combine position vector to another position vector is by using what we call the homogeneous transformation matrix. So I will discuss it to the next video.